Let's open MATLAB and let's start to learn how to code a digit classifier based on image processing and convolutional neural networks. And this will be done in 4 steps. First, we will load and visualize the data sets. Second, we will define the model architecture. Third, we will train the model. And fourth, we will use the trained convolutional neural network to recognize digits in new images, or in other words, to make predictions. Let's upload the digit dataset zip file containing the dataset we will need and the MATLAB functions load data, show random sample, and visualize digit prediction. And these tools will be useful to read, visualize, and store images in matrix form. We extract the contents of the digit dataset file using the unzip command, giving the file name as input and pressing enter. The folder we extracted contains images from the open source MNIST dataset, which consists of 28 by 28 pixels grayscale images of handwritten digits from 0 to 9. Each example in the dataset includes an image and its label indicating which digit it represents. We will use 2 separate datasets, one for training the model called training dataset, and one for evaluating its performance called validation dataset. So let's start with the training dataset. To load it, we first create a new script and specify the path to the folder containing the images and their labels. And we then use the load data function to store the matrix representation of images in xtrain and the corresponding labels in ytrain. So let's start to explore our dataset using the function show random samples. And this function randomly picks 4 images from the dataset we just loaded and shows them. The first parameter specifies the path from which we're picking the images, while setting the second one tells the function to display the images containing, in this case, the digit 5. It is convenient to first set the random seed for reproducibility, and this forces the random number generator to produce a fixed sequence of numbers each time the code is run. So here are 4 examples of the digit 5. Next, we prepare the validation set in a similar way by calling the same loading function. Only this time we use a different path, so validation set is the folder containing additional images that will not be used during training. And then, using again load data, we store the images in X validation and the corresponding labels in Y validation. Let's see how many images both datasets contain. Using the size function on xtrain and X validation, we can see how many samples each dataset contains. But these are 4D arrays because images are 3D arrays. So to get the number of images, we look at the 4th dimension of the array, passing the argument 4 to size. While to inspect the size of a single image, again, we use the size function applied to xtrain, but this time we look at the first 2 dimensions, indicating the height and width of the images. And we see that the training dataset contains 9,990 images made of 28 by 28 pixels, while the validation dataset contains 1,000 images. And now let's address the second step, the definition of the architecture of our classifier. And the idea is to concatenate all the layers defined by specific MATLAB commands to create the final architecture. First, image input layer informs the convolutional neural network about the size of the input image. And in this case, the size is 28 by 28 pixels times 1 color channel. And the following convolutional neural network layers are defined using functions provided by the MATLAB Deep Learning Toolbox. We have convolution 2D layer to define the convolutional layer, and its activation function is applied separately by the function ReLU layer, which follows convolution. Next, max pooling 2D layer, implement the pooling layer. And the output of the pooling layer is reorganized into a vector thanks to flatten layer. And finally, fully connected layer defines a dense neural network. The classification task is then completed by calling the softmax activation function in softmax layer and converting the resulting probability into classes with the classification layer. And it's important to note that the arguments to these layers are design choices that depend on the problem. They are usually fine-tuned through trial and error. And in this example, we present you one specific configuration, but we encourage you to explore different ones and see how results change. So let's see in detail how to define these layers, starting from the convolutional one. The first argument to the convolution 2D layer is the dimension of the filter. And in this case, both height and width are set to 3. And the second argument, 32, defines the number of filters. The padding option, same, ensures that the output has the same dimension of the input image. And as a result, the output of the convolutional layers are 32, 28 by 28 matrices. And it's worth noting that since each layer has 9 learnable parameters, we have 9 times 32 learnable parameters to be optimized so far. But we will come back to this later. We then set the activation function to ReLU to keep the output positive. And next, we apply max pooling. And in the argument, we define the pool size, which in this case is 7 by 7. And we also add a stride of the same dimension, meaning that we move with a step size of 7. And this reduces the dimensionality significantly, so 28 by 28 matrices are reduced to a size 4 by 4. And at this point, we want to convert this set of matrices into a vector format that the dense neural network can receive as input. And this process is done by the flatten layer. And note that this layer does not perform any computation on the data. It simply reshapes it, transforming the set of 32 small matrices into a one-dimensional vector with 512 elements. The dense layer is then the last layer in our convolutional neural network architecture. The argument 10 defines the number of output neurons corresponding to the possible classes in our classification task that are the digits from 0 to 9. We then add a softmax layer that converts the output score from the dense layer into classification probabilities. And finally, the classification layer computes the cross-entropy loss function for classification tasks. And we have now finished defining our convolutional neural network architecture. But remember, along our way, we have seen many unknown parameters that must be found. They are the filtered entries and the weights and biases of the dense layer. And this is the task for the training process, which, remember, is an optimization problem in which we try to minimize the loss function. And to do it, we begin by setting the training option using the training option function. The first argument selects the optimizer, and in our case, we use the stochastic gradient descent method, here abbreviated as SGDM. And the second argument defines the learning rate, which is here set to 0.01. And we choose to perform optimization using a mini-batch approach. And this means that at each optimization step, the network only processes a small subset of the dataset called a batch. And once the optimizer has seen the whole dataset, we say that the training epoch is completed. In our case, we set the number of epochs to 20 and the batch size to 16, meaning that the model updates its learnable parameter by processing 16 examples at a time. We also allow shuffling at every epoch, meaning that the mini-batches change during training. The sixth argument is used to provide validation data, and the 7 enables a live visualization of the loss function during training. And finally, the verbose argument is set to false to limit the amount of printed text. So we are ready to start the training process. The train network function starts the training process, and its arguments are the training data that consists of images containing xtrain and their labels containing ytrain, and converted into categorical variables with the function categorical. We then have the architecture of the network defined in layers, and the training options defined in options. And here's the output of the code. In the top figure, we can visualize the accuracy of the model on the training dataset, which is the blue line, and on the validation dataset, the black line. While in the bottom figure, at each optimizer iteration, the code displays the value of the loss function on the training dataset, orange line, and the validation dataset, the black line. And by the final iteration, we can see that the model reaches a very satisfactory performance. So we have about 97% accuracy on the validation dataset. We could also compute accuracy by using the function classify and giving as input the validation images. The predicted categories are stored into the array ypred, and then we check how many times the classification is correct by comparing ypred to the actual labels in yvalidation, getting 1 if they match and 0 if they don't. The sum function then counts the number of matches, which is then divided by the number of validation samples counted by the numel function. And as you can see, about 97%. Now we're at the fourth step, so let's look at some results using the function visualize digit predictions. And this function visualizes one randomly selected image, in this case of the digit 3, and displays the prediction probabilities made by the network for each different digit. And for this sample, the model correctly classified the image as a 3 with 99% confidence. So let's try with another image, this time of the digit 5. For this other validation example, the model correctly classifies the image as a 5, but only with a confidence of about 57%. But interestingly, it also assigns a 37% probability to the digit 3, indicating that there is some uncertainty or confusion between the two classes. And in this case, as a human, I would be confused too.